All right, before we start talking about the photoelectric effect, it's time to review a little bit about what we remember about light, energy, and photons. What you can see here on the right is an example of light being dispersed by a prism, undergoing refraction, making a visible spectrum of light. And when that light will turn to its side, we'll be able to see the absorption spectra. This is stuff we learned in nuclear physics and in waves. We should be able to explain what those black lines are. Those are the wavelengths of light that are being absorbed to excite electrons from one energy level to the next. So what light is light is a form of electromagnetic radiation, and it travels in waves. What we know is that it's an oscillating electric and magnetic field, like you can see over here, and it doesn't require a medium to transfer. And the wave properties of light are confirmed because they reflect, refract, and diffract. All waves do these three things, and that's why we know that light is a wave. Here's just a good example of the electromagnetic spectrum and what we should remember about it. You should be able to remember all the different frequencies and bands. So we got gamma rays, X-rays, UV light, visible light. And we just got to know that the high energy ones, the gamma rays, have high frequency, and the low energy has low frequency. In contrast, the low energy has long wavelength, high energy has short wavelength, and we should remember these formulas to be able to calculate the energy of light, where h is Planck's constant, c is the speed of light, and lambda is the wavelength, f is your frequency in hertz. So what we should also remember is how light interacts with atoms. So when incoming wavelengths of light are coming into an atom, not all of that light will be absorbed. Different atoms, if we remember from the absorption spectra in the nuclear physics unit, different atoms will absorb different quantized amounts of energy to excite an electron from the ground state up to different energy levels. That's the level up over here. So only quantized amounts of energy are absorbed, and very specific wavelengths will be absorbed just to be able to excite those electrons up to different levels. Again, that's the formula that we'd use, and Planck's constant is over here, 6.63 times 10 to the minus 34 joules per second. So let's just do a quick practice problem, because in this section where we're going to be learning about the photoelectric effect, we have to be able to calculate the energy associated with light in joules and electron volts. So let's remind ourselves how to do that. You can pause the video and do that yourself, and then here's the answer. So in order to do this, to calculate the energy of 400 nanometers of light, I have to plug it into my formula. It's in wavelength already, so I'm going to use this formula, where this is 6.63 times 10 to the minus 34 joules seconds times the speed of light, which is 3 times 10 to the 8 meters per second, divided by 400 times 10 to the minus 9 meters. Okay, when I plug that into my calculator, I'll find out that the energy is equal to, the energy is equal to 4.96 times 10 to the minus 19 joules. Now, how do I convert that into electron volts? Well, I need to remember that 1.6 times 10 to the minus 19 joules is equal to 1 electron volt. So in order to convert that, I have to divide this number by that in order to get how many electron volts there are. So 4.96 times 10 to the minus 19 joules divided by 1.6 times 10 to the minus 19 joules per electron volt gives me 3.1 electron volts. Now, knowing that I can remember how to describe light, and if I can go back and calculate the wavelength and frequency and energy associated with any of these wavelengths of light in the electromagnetic spectrum, I am ready to move on to learn about the photoelectric effect.